Hi, in this video, we want to take a look at the binomial distribution. All right, so the binomial distribution is where we have several Bernoulli random variables being added together. Now, something that's very important about this is that the Bernoulli random variables are independent and identically distributed. Big aspect of this. Everything hinges on those two. Independence means that for each Bernoulli event, remember, Bernoulli events are one of two values, and we're going to code them as 0 or 1 for here. That 0 or 1 each time is independent of all the other Bernoulli random variables that are going on. And we have the same probability of a 1 every single time. Okay, so let's think about a motivating example. Let's say that you're working at a company, you go up to an assembly line, and you want to do a quality assurance check to make sure you're not sending out bad product. You know, like the machines may be getting worn down, people may not be paying attention like they should be, maybe the components that you're bringing in are poor quality and you don't know it. So what you do, you go and you check and you make sure that the output from your assembly line is looking good. All right, so it's standard in the industry to kind of have like a standard protocol that you do every single time. So you walk up, and for your protocol, you're going to pick 5. You're going to randomly pick 5 of them, and you're going to check to see if any are defective. Well, you see 1 is defective, 4 are not defective. Okay, well, is that too many defective? You've got 1 defective. You need to make a decision. Is that too much? Should we shut things down and start checking to make sure, do we have any problems? Does anything need to be repaired? Do I need to check quality of components? Or is that okay to let go? Well, one thing you would want to consider is what percentage of defective items is acceptable. All right. And so what we would do is to see if that, to kind of get our hands or to get our heads wrapped around this, we would use a binomial distribution to model how likely 1 or more defective items would be with a situation of in Bernoulli trials of 5. The probability of defective is 0.01, and here x is equal to 1 because that's how many defective we have. And so we look at the probability of 1 or more defective, and if that is too large, then we're going to go, hey, we need to shut this down. Okay, so the binomial distribution. So fundamental to this is that this is the sum of Bernoulli random variables where we add up the 0s and 1s. We have the same probability of 1 every single time, and all of the Bernoulli random variables are independent of each other. All right, so for us, the formula, the probability of having x successes, remember when we talk about Bernoulli random variables, we say success is a 1, failure is a 0. All right, now when I say success, it means we code it as 1, failure means we code it as a 0. So in that defective, in the defective case, I would count the defective 1 as a success, the 4 that were non-defective as a 0. Those would be called a failure, which is kind of a peculiar way that we word it, but that's just how we do it in statistics. All right, so the probability of x successes is going to be n choose x. So here this is a binomial coefficient, n choose x, p to the power of x times 1 minus p to the power of n minus x. Okay, so some things you'll notice. N is up top, x is down here. You'll notice that the exponents here, the x and the n minus x, those add up to n. And you'll notice that the p and the 1 minus p add up to 1. Okay, so just something to try. That's something I always try to remember as I try to remember the formula. Okay, so in this situation, the expected value is n, so the number of Bernoulli random variables times the probability that each individual Bernoulli random variable will be 1. What is the variance? Well, it's n times p times 1 minus p. And if you remember the Bernoulli random variable, you'll go, hey, if I replace n with 1, I'll get exactly the Bernoulli random variable distribution, and you'd be correct. All right, so remember that x is a random variable between 0 and n. N is the known value. So remember, n is a known value, p is a known value for this. P is the probability. And here's the formula. Remember when we talk about factorials, if I have like 5 factorial, that's 5 times 4 times 3 times 2 times 1. All right, and remember 0 factorial is equal to 1. All right, so for us to be able to use the binomial distribution to model an event, we need the following to be correct. 1, the event has to consist of a fixed known number of identical trials. Each trial results in one of 2 possible outcomes, success or failure. The probability is constant from trial to trial. The trials are independent, and the random variable is the number of successes among the n trials. If we have this situation in real life, this is a good situation for us to be modeling with the binomial distribution. All right, so now let's take a look at this formula. Why is it that this defines a probability? Remember, a probability, the function, first of all, it's a function. It's always non-negative values. For a discrete probability, they're always between 0 and 1, and they always add up to 1. All right, so if I'm looking at this mamma jamma ugly thing, why do I think that this is going to add up to 1? Okay, well, first thing we're going to do, I'm going to say we're not going to really worry about when p is 0 or 1. When p is 0 or 1, that's a very weird special case. I'm just going to skip that. So let's take care of the case where it's just like a half, 0.53, 0.75, any number besides 0 or 1. All right, so what we're going to do to be able to see that this actually defines a probability for us is that we're going to use the binomial theorem. Is that surprising that I'm using the binomial theorem in the binomial random variables? I hope not. All right, the binomial theorem from pre-calculus, if you remember it, if you don't, here's a review. A plus B inside the parenthesis to the power of n, all of this is equal to this formula over here, where I have a to the power of I, b to the power of n minus I, times the n choose I, the binomial coefficient, and then I add up, going with I starts at 0 all the way up to n. It's an ugly formula. I know it's got, you know, a summation symbol in there, kind of overwhelming. All right, so this formula is true and correct for mathematics. Now, how do I apply this to the binomial distribution? What I'm going to do, I'm going to replace A with P. I'm going to replace B with 1 minus P. Okay, so here I'm going to replace this A with a P, this B with 1 minus P, and I do the same here. This becomes a P, this becomes a 1 minus P. All right, so this becomes, the left-hand side of the equation becomes P plus 1 minus P to the power of n. Then I have the binomial coefficients times P to the I times 1 minus P to the n minus I. And then I add up I going from 0 to n. Okay, well, so the right-hand side, this looks like adding up the terms in the probability. Okay, so here we see that we have the probability aspect that we previously looked at already locked down. What's happening on the left-hand side? Well, P plus 1 minus P is better known as 1. Easy arithmetic, right? And then 1 to the power of n is 1. So I can see that, yes, this actually does define a probability. Okay, so now Anytime I talk about a random variable, next thing I always want to talk about is the expected value. After that, I talk about the variance. Remember, when I talk about a random variable, the expected value is kind of like the one number summary of the random variable that gives me the most information. Variance is like the second stringer. All right, so to compute the binomial random variable, what I want to do, what I could do, I could sit down and start using the expected value formula. And remember, that's going to have a summation. I'm going to do x times the probability of x, add them up. I can do it that way. But there's an easier way, and I'm lazy. I want to do this the lazy way. What am I going to do? You know what? I'm going to remember, this is in fact the sum of other random variables. So what I'm going to do, instead of taking the expected value of the random variable I'm working with, I'm going to take the expected value of the sum of other random variables. So here, the number that my random variable is the sum of successes. Adding up the zeros and ones from the Bernoulli random variables. All right, so I'm going to add up the Bernoulli random variables coded as 0 or 1. And then, I've got the expected value going on both sides. Okay, so now, remember, expected value comes from integration. Well, if I'm doing a sum, so if I have a summation inside an integration, I can break it up into the sum of integrals. All right, so if I do that, if I work with that just a little bit, if I carry that out just a little bit further, I can see that this expected value is the same as this expected value summation. So the expected value of the sum is the sum of the expected values. The reason why I can switch it like this is because of integration. This does not always work for all possible operations, by the way. Okay, so now I've got that the expected value of x is equal to the sum of the expected value of the Bernoulli random variables. Now, they all have the same probability, which means they have the same expected value. So I just plug it in. Boom, I have a bunch of p's. What do I do when I add something to itself repeatedly? I convert it to multiplication. And so we can see the expected value is n times p. Boom, we got this. Now, let's think about variance. I'm going to do the same trick here, but the justification for my line-by-line work is slightly different because variance involves a squaring term. Okay, so x is the sum of the Bernoulli random variables. Remember, they are independent, identically distributed. So the variance of x is equal to the variance of the sum of the Bernoulli random variables. Okay, so something that I haven't talked about in any of the videos before is that if I have independent random variables and I take the variance of the sum, the variance of the sum of independent random variables is the sum of the variances. Something that's very important is that this does not work out in general. The expected value, it doesn't matter if they're independent or not. It works out either way. We don't care. It's fine. The reason why it's an issue here is that because I have a squaring aspect. If I was to sit down and start doing this integral the full proper way using x minus mu squared inside integration, something that would come up is I would have the product between b1, b2, b1, b3, b1, and so on. And I would have that twice every single time I could have a pair. So it's going to work out that because of independence, we have covariance of 0 between different Bernoulli random variables. The integral of the product of the two values is going to give us a covariance. And so something that's very important is because of independence, those multiplication terms give us 0 if I go through the integration. But for us, we're not going to worry about it. So the variance of the sum is the sum of the variance. The main thing to remember is that this is only true because of independence. Okay, so now once I get to here, I realize that, hey, all the Bernoulli random variables are identically distributed. So this means that they all have p times 1 minus p as their variances. And so I just replace it. Boom, I've got this. And now repeated addition is better known as multiplication, and boom, we've got it. All right, so something that can jump out at us is if I have a given p, if I increase the number of trials, that will increase my variance. Also, if you remember from the Bernoulli random variable video, I showed that this is maximal at when p is equal to 1/2. And so it doesn't matter what the n is. If I have a binomial random variable for a fixed n, I have maximum variance when p is equal to 1/2, 50-50. Hopefully that is intuitive to us. And we get the most variation, the most spread of my zeros and ones when it's equally distributed. Things don't get clumped up. All right, so now next thing is to talk about using the binomial distribution inside R. All right, so remember, R always gives us a density, a probability, a quantile, and a random number generation function. So remember, the density is with D, the cumulative distribution function is P for probability, quantile is Q, and random number is R. And what it's going to be is it's going to be the binom every single time. So for density, it's going to be D binom. And then, well, I'm going to talk about the parameters real quick. So X and Q are vectors of quantiles. P is a vector of probabilities. N is the number of observations. So here, that's for random number generation. Size. Now, so everything I've been talking about previously, I had an N. Inside R, that is size. And prob is the probability of success on an individual trial. Okay, this part right here is used just to suppress an output so we don't get blasted in the face with numbers. All right, for the density, D binom, if I want to know the probability of 5, when I have 10 trials and 50-50 chance, I can see that it's a 1/4 probability. All right, if I want to have the cumulative distribution function, Q is the quantile, so here I'm going from 0 to 10. Size is the number of Bernoulli trials, and prob is the probability of success on an individual trial, and R spits out the cumulative distribution values for us. Now for quantiles, Q binom, we pass P, these are the probabilities I'm interested in, and here I just picked the standard quantile ones. Here, remember, size is the number of Bernoulli trials, and prob is the probability of an individual trial being won. And here I get the quantiles. And then for random number generation, it's R binom. N is the number of randomly generated values I want spit out at me. Size is the number of trials in each individual number, and probability is the probability of a 1 for each individual trial. Now, look at my numbers down here. Something you always want to do whenever you use a random number generation, make sure that the output looks like what you want. Here, I've got N is equal to 100, and I see that I have 100, or well, I have approximately 100 numbers here. All right, this 1 says that that 3 is the first observation. This 38 says that this 5 is the 38th observation. 75 says this 4 is the 75th observation. And so if I want to, I could go through and count and make sure that I have exactly 100. So when this comes up, when you're working with R, you can play around with these parameters to make sure the output is giving me what I wanted. If I would have only seen 10 numbers out, I would have known I had things reversed. Now, when I look through here, I'll notice that all the numbers are between 0 and 10. Is that how I intended it? Yes, it is. Now, also, just empirically looking at it, you'll notice that I don't have any zeros, I don't have any 10s. So if I was to go up and start looking at the probability of 0 in this situation, probability of 10, it's probably very, very small. Actually, we can look at the probability of 10. If I scroll back up here, the difference between these two numbers will be the probability of 10. That's pretty darn small. That's less than 0.001. And here's the probability of 0. That's pretty darn small. Here's a 1. Is there a 9? I don't see a 9 looking at it right now. Oh, there's a 9. So we can see that, there's some numbers there, but it's centered mainly at 5. And we'll talk more about that later. All right, now for your assignment for this lecture, what we're going to do, we're going to take our textbook and we're going to solve some problems. Go to page 58, do 32, 33, 34, 35, 36. Put it in a document, include your code, and submit it to Canvas. That's all I've got for you. Take care and goodbye.